So this lesson is going to be connecting infinite limits and vertical asymptotes. So we're going to start off by completing this table, and I just want to remind you of how you can do this in the graphing calculator. So what you'll do is go to y equals, and you're going to type in the function. Now, sometimes we want the decimal and not a fractional answer, so I think on this one it's going to be easier if we don't use the alpha y equals tool, that we just type it in like a fraction, but we have to be really careful. The denominator has two terms, so we're going to need to make sure we put the x minus 2 in parentheses. If the numerator had more than just the 3, like if it had been x plus 3, we would have to put that in parentheses divided by the denominator in parentheses. All right, so we can go to the graph. And I don't really want the graph, I want to fill in this table. So what we're going to do is calculate a value. So to calculate anything, you do second trace to get to the calculate menu. And calculate a value is number 1. So what I would do is going to start on the left, I'm going to type in 1.9. That's the value for x. And then for the y, you're going to get negative 30. So go ahead and fill that in for y. Alright, and we don't have to do the second trace every time. Now I can just type in 1.99 and then I'll get a value. So you guys finish that table. So remember, it's second trace and then number 1, and then you start typing in the x's that you need. Alright, so when we put in 2, we get 3 over 0, so there isn't a value for the function when x is 2, but we can find the limit as x approaches 2 from the left. Alright, so what happens is that number just keeps getting smaller and smaller and smaller. So you could guess if we typed in 1.9999, it would be negative 30,000. If I added another 9 at the end, it'd be negative 300,000. So that graph or function is approaching negative infinity, continuously getting smaller and smaller and smaller. Alright, so let's see what happens as x approaches 2 from the right. Alright, so this time from the right, the values of the function are getting bigger and bigger and bigger the closer you get to 2. So again, you could guess if we wanted to find the value at 2.0001, it would be 30,000. It's just going to get bigger and bigger the closer you get to 2. So that graph is approaching infinity from the right. Now, I don't want you guys to think that because we're writing down that the limit equals infinity or negative infinity, that means the limit exists, because it doesn't. Infinity is not the value of limit. So it still doesn't exist, but you're stating how it does not exist. So let's jot that down. So the limit still does not exist. But we're stating how it doesn't exist. Alright, so let's give the definition of a vertical asymptote. if the function f of x approaches infinity or negative infinity as x approaches a real number. Let's call that number c. From the right or from the left, then x equals c is a vertical asymptote. Alright, so as long as we're approaching a real number like we were here, and we were here, and we end up with infinity or negative infinity from either side, then there's a vertical asymptote at that real number. Alright, and so I put in a graph, and as you can tell, here's 2. As we approach 2 from the left, it's going to go down, down, down forever, which is negative infinity, which we already knew. And when we approach 2 from the right, it's going to go up, up, up forever, which is positive infinity, which we already knew from the table. Alright, so just a reminder, and we talked about this, direct substitution of a rational function will yield something like 5 over 0 or negative 2 over 0 at a vertical asymptote, some kind of non-removable infinite discontinuity is the same as a vertical asymptote. And you can find the one-sided limit of a vertical asymptote is going to either be going to infinity or to negative infinity by plugging in values on one side of the vertical asymptote. So depending on what side you're in, you just plug in a value. You get a positive number that is approaching positive infinity. If you get a negative number, it approaches negative infinity. And that's just talking about finding the one-sided limit at a vertical asymptote. So you would need to already know that you're getting a real number over 0 that is going to be a vertical asymptote. Alright, then also, and I think you guys already know this, direct substitution of a rational function will yield 0 over 0 or indeterminate form at a whole or a removable discontinuity. Alright, so what we do is we further investigate by factoring and canceling or some other algebraic method to find the location of the whole. Alright, so on example 1, we're going to find the vertical asymptotes, if any, and any removable discontinuities of the function. Alright, so we're not given anything except the function, so we don't know where it is right now. So we have no idea until we start factoring. So go ahead and factor the numerator and denominator. This is going to take a little bit. There's several steps to factoring this one. So here in this denominator, we're going to want to factor by grouping. We're still not quite done. One more step, x squared minus 9 will factor one more time. Okay, and this takes us back to pretty much what we learned in pre-calculus about rational functions and wholes and asymptotes. So anything that cancels, a factor that cancels, creates a hole in the graph. So that we're not calling it holes in the graph for this one, we're calling removable discontinuities. So I know for sure I have removable discontinuity when x is equal to -3 and when x is equal to 2. And then anything that doesn't cancel out, that's still in the denominator, creates a vertical asymptote. And that's going to be when x is 0 and when x is 3. All right, and then we can go back and show that by using the rules we talked about here. That for the vertical asymptote, when I plug the value into the function, I should get some number over 0. And then for the whole, then I should get 0 over 0. So let's just start with 0. F is 0. If I put 0 in for all the x's in the numerator, I get -24. In the denominator, I get 0. All right, when I put in 3, in the numerator, I get 24. In the denominator, I get 0. That's what happens for vertical asymptotes. All right, and then for the removable, I said I had one at -3. When I plug -3 into the numerator, I get 0. Denominator, I get 0. And then 2, again, I get 0 over 0. And that's just plugging into the original function. So that shows that we have removable discontinuity. Okay, there's a whole lot of factoring on that one. All right, and then the second example, I have 4 parts. They're all a little bit different. And we're going to find some one-sided limits. In this first one, we're going to find the limit as x approaches -1 from the right side. And we're going to just use the graph. If you have the graph available to you, please use the graph. So -1 is right here. So I'm going to come from the right side because I have that plus. I'm going to approach -1. So because that graph is going up, 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 up forever, the limit is going to be positive infinity. All right, so let's look at B. B, we don't have a graph. So we're going to start off with direct substitution. So if I plug in 1 for the x, I'm going to get 1 over 0. 1 over 0 means we're going to have a vertical asymptote. So let me just go back and remind you what we wrote a second ago. So if direct substitution yields something like what we just got, 1 over 0, we have a vertical asymptote. You can find the one-sided limit. You can find the one-sided limit to infinity or to negative infinity by plugging in values on one side of the vertical asymptote. All right, so I'm just going to do this little table of values. All right, so since I'm approaching 1 from the right side, I'm going to plug in a number really close to 1, but on the right side of 1. So I'm going to plug in 1.1. And I don't have to know exactly what it equals. I really just need to know if it equals a positive number or if it equals a negative number. All right, so when I plug in 1.1, so it's a number that is on the right side of 1, I'm going to get 1 over 0.1. That's a positive over a positive is going to give me a positive. So because I got a positive value, that means that the limit as x approaches 1 from the right of that function approaches positive infinity. So we already knew there was a vertical asymptote. So we wanted to find the one-sided limit, so we checked a number on the right. We got a positive, so that means from the right side, the graph is approaching positive infinity. Okay, so let's look at the next one. This one, I want to use some properties of limits to separate this. I'm going to find the limit as x approaches 0 from the left of 1 plus the limit as x approaches 0 from the left of 1 over x. Now, when we find the limit of a constant, it's just going to be equal to that constant. So I know I have 1. All right, and then I also know that when I do direct substitution on this one, that I get 1 over 0, and that tells me that I have a vertical asymptote. So I need to figure out if that side of the graph, if we're approaching 0 from the left, if we're approaching infinity or negative infinity. So I'm going to do my little table. I'm going to do it over here. And I'll just put in a number that is on the left side of 0, so negative 0.1. So 1 over negative 0.1. That's a positive divided by a negative is definitely going to be a negative. So that means that that graph is approaching negative infinity because I knew it was a vertical asymptote. I plugged in a number on the left side and I got negative, so that means negative infinity. So think about it. If you have 1 and you subtract infinity from it, is that 1 even going to touch it, like change it remotely? It isn't. So 1 plus negative infinity is the same as just negative infinity. Alright, so let's look at this last one. We plug 3 in, negative 3. Negative 3 plus 3 is 0. And then on the denominator, it's going to be negative 3 squared is 9, minus 3 minus 6 is another 0. So I know from what I wrote before and what we've talked about several times that if we have a rational function, we get 0 over 0, that we are going to have a removable discontinuity. And I need to further investigate because the limit is going to exist. It's not going to be infinity or negative infinity. It's going to be just a regular old number. So to further investigate, we're going to factor the denominator. Okay, so because that x plus 3's cancel out, that leaves me with a 1 in the numerator. So I can go ahead and plug in the negative 3. So that value of that limit is negative 1/5. So you do one-sided limits like that, like we did two-sided limits by plugging in. Because the one-sided will equal the whole limit. All right, so let me give you guys your assignment. On page 88, I want you to do 2 through 8 even, and then 14 through 30 every other even. And then go back and do 29. And then 34 through 40 even.